This is going to be awesome.
How reactor make city go burr. Magic fission make rock get hot. Hot rock heat water. Hot water heat other water, make boil, make steam. In boiling water reactor, hot water and other water, same water. Steam water turn fan. Fan turn magnet. Turning magnet make electricity. Electricity make city go burr. Magic fission make rock get hot.
So how exactly does fission make rock hot? Before we get into that, we need to know what is hot and what is temperature. Technically speaking, the temperature is the average molecular kinetic energy of a substance. But more simply put, it's basically just the measure of the movement of the molecules and atoms in a substance. So the more movement that you have of these molecules in the substance, the higher the temperature. If you've ever learned how a microwave works, you know that the microwaves come in and it causes those water molecules to vibrate around. And that increases the overall movement of the molecules and therefore kinetic energy of the substance to increase, and it makes the temperature increase. I'll explain exactly how fission works in another video, but in this one I want to explain how do these products over here cause the temperature to increase in a uranium pellet. So after fission happens, it creates these fission products. It's either 2 or 3 different products that are a smaller size than the original uranium atom, as well as some neutrons, and it doesn't show it here, but there's going to be some gammas that are produced as well. If you were to add up the mass of all these products and include the gammas, doing a conversion from energy to mass, of course, it would not equal the mass of this neutron and uranium atom that it started out as. So what happened to that mass? Well, it went into the kinetic energy and the movement of these molecules. So mass was converted directly into energy from fission. Now what happens with the gammas that are produced with this, it'll be absorbed in the overall surrounding material, and it will cause the electrons to be knocked off of the different atoms. Those electrons will go around and bounce on other atoms, and overall will increase the kinetic energy of that substance. Neutrons, those are going to do a similar thing. They're going to go and knock around on the different atoms and cause a lot more kinetic energy movement. They'll get absorbed in some of the atoms, and some of them will leak out of the core entirely. Now, these fission products, they have a lot of kinetic energy. They do have the most kinetic energy, and they'll bounce against the other atoms that are nearby, causing them to move around and overall increase the movement and the kinetic energy. This means your temperature increases, therefore makes rock hot.
The size of an isotope, which is basically just a flavor of an element, determines whether or not it's going to be able to fission. So if you have a very large element that's having trouble trying to stay together into one mass, it can fission. So here you have your chart of the nuclides. As you go higher and higher on this chart, you have more protons. If you go this direction on the chart, you have more neutrons. Zoom in here, you can see hydrogen. It has only 1 proton, then 2 protons, 3 protons, and these are your flavors, your isotopes of your different elements. So as you zoom up here, like I said, you're going to get higher and higher on it, more protons, more neutrons, and you can zoom into these heavier elements here. In order to fission in a reactor, you actually need to be up here in your uranium level and higher. And like I said, when you have that many neutrons and protons in an element, those nuclear forces have a lot of trouble trying to keep all of those neutrons and protons together to where it wants to split up. So here's an animation I found of a neutron coming into this nucleus. And what it does is it makes it just slightly too large, just over the edge. And that causes it to behave like a liquid drop, and it just doesn't want to hold together. Those electrical forces of those protons causes it to want to repel against each other until it splits into these 2 elements called fission products and neutrons. In a fission reactor that's operating at normal self-sustained reactions is at criticality. That means that one of those neutrons will go on to another uranium element, cause it to fission, which produce more neutrons. One of those will go on to another one, and you have criticality.
I love this question, and I think I'm going to answer it the way you want me to. So, when a radioactive material atom decays, what happens to that radiation that comes out of it? The big question we have here is, what type of radiation are we talking about? I'm going to, for simplicity's sake, talk about alpha, beta, and gamma decay. The gammas that are produced, they can interact in three main ways: the Compton scattering, photoelectric effect, and pair production. By the way, a incident photon, that is a gamma. A gamma is a type of photon. In all of these interactions, a fast electron can be produced. These are slightly different because this one here produces a scatter photon at a lower energy than the initial one. Pair production, when you have a high energy gamma that interacts with the nucleus, it can produce both a positron and an electron. The electrons produced in that interaction are going to go on and interact like beta decay. The positron, however, is going to go out and seek an electron because it is the opposite as an electron. And it's going to circle around that electron. They're going to get closer and closer to each other until they meet in the middle and annihilate. They will turn completely into energy, which is in the form of two photons traveling in the opposite direction. For those electrons that are knocked off by those gammas, as well as the betas that are produced in beta decay, they're going to interact in several different ways. One of the really common ways is to interact with the electrons surrounding other atoms. It can cause some of those electrons to get knocked off, like this one here, which those can go on again to interact with other electrons. And then what will happen is one of these outer electrons will decay down into this lower orbital and produce an X-ray. That's how X-rays are produced. Another thing that can happen in high energy electrons is it can go around the nucleus of an atom and it will be redirected because of the positive pull on that electron from the nucleus. This will cause Bremsstrahlung to be produced, and that will go on to interact like gammas. Now, like an electron, alpha particles will also interact with the electrons in the surrounding material, but it will interact with a lot of electrons at the same time because it has a stronger negative charge and it's a much larger molecule. This means that it will also travel a much shorter distance. Imagine a person jumping into a ball pit. They'll be interacting with a lot of balls at one time and slowing down very quickly. So what happens to all of that radiation once it's done all these interactions? Well, all of them are going to basically increase the overall movement and kinetic energy of that substance after it's become completely absorbed, and it will increase the temperature. Those alpha particles, once they've slowed down, they'll turn into helium.
In boiling water reactor, hot water and other water, same water.
So why back in the day did they decide to build two different types of light water reactors? Just to recap, we have the pressurized water reactor and the boiling water reactor. In the pressurized water reactor, we have this primary loop here that is kept isolated from a secondary loop that turns the turbine and gets sent back into the steam generator. Yes, I said turbine. That's the way we said it in the nuclear navy. Now, in the boiling water reactor, we have the boiling happening right in the core here and then sent to the turbine and then condensed and sent right back into the reactor. So why have the two different types? Well, there's advantages and disadvantages with both these kinds of reactors. One of the main advantages of the pressurized water reactor is that these systems over here do not become contaminated at all because there's a pressure boundary and these liquids do not mix. During normal operations, there is slightly contaminated water that flows through this loop and it never gets into your steam system. Now in the boiling water reactor, there is no pressure boundary, so it goes directly into these components over here. Now there is some separation of the contaminants in the reactor vessel itself, but low levels of radioactive material make it into the system and make it contaminated. This makes the maintenance a lot more complex than these systems over here. It also increases the dose to the workers. Now the big advantage with the boiling water reactor is just how simple it is. The reactor is the steam generator as well. Over here you have to build an entire primary system and separate steam generator.
Now this also introduces another complexity. The reactor vessel over here, this whole pressure vessel, needs to be a lot bigger than the pressure vessel over in the pressurized water reactor side. There's some other differences between these two reactors that I didn't mention here, but a lot of it really has to do with the preference of the utility and the operators that are operating it. Now, I myself could go really either way with these different types of reactors. I know that with the pressurized water reactor, that's something that I operated when I was in the Navy, so I'm very familiar with it. On the boiling water reactor side, I love the simplicity of it. Now, which one would you prefer?
Fan, turn magnet. Turning magnet, make electricity.
So how does a steam turbine connected to a magnetic generator create electricity? Which, by the way, it's called a turbo generator, which you can buy on eBay for $79,000. So let's start out with, how does a steam turbine work? This is me here standing in front of a turbine. This is a low pressure turbine at the Kewaunee power plant. It's actually not really a power plant anymore. It was shut down a few years ago. I took this picture just a couple weeks ago at a tour, but this turbine is basically just a fan, like I said in my previous video. The steam is going to hit these blades and turn this entire turbine just like you would see at a wind turbine. After the steam comes out of the steam generator, it's going to first pass through a high pressure turbine. Then it's going to go through what's called a moisture separator reheater, where it removes any of that moisture that gets built up in the high pressure turbine and also heats that steam back up. Then it's going to go into your low pressure turbines. At the Kewaunee plant, they used to have 2 low pressure turbines. Those low pressure turbines are always going to be a lot bigger than the high pressure turbine. You can barely see it here because that steam expands as the pressure goes down. So you need a bigger turbine to handle that expansion. All of these turbines are coupled to each other to turn this generator that has those magnetic coils in them. And yes, I said turbine because that's the way a lot of people in the nuclear field say the word. So how does that generator make electricity? I mentioned before it's a spinning magnet, right? A spinning magnet, or a magnet moving in the presence of a conductor, will cause the electrons to flow in that conductor. In this case, it actually shows the conductor moving and the magnet staying the same, but it's the same principle. This here shows the spinning magnet in the center. And when the magnet is closest to the conductor, that's when the highest current is going to be, and therefore the highest voltage. Here you can see the black coil conductor is closest to where the north and the south pole of this magnet is, therefore the highest voltage is. As that magnet rotates, the voltage will go down. When that magnet is completely perpendicular, it's actually at 0. And when that magnet is completely upside down, that's when the voltage is at its minimum. This cycle continues to happen, and that's why you have AC current. And if you spin that magnet in the center at just the right speed, you get either 50 Hertz or 60 Hertz, depending on what part of the world you're in. And that's how a turbine generator works.